Please give a warm welcome to Dr. Angela Belcher.
Good morning. I'm excited to be here to tell you some of what I've been thinking about in terms of evolving organisms to make new materials. And I brought an example with me today, which is an abalone shell, which you can see it's an amazing biocomposite material that's 98% by mass calcium carbonate and 2% by mass protein, yet it's 3,000 times tougher than its geologic counterpart. Not only that, it makes it in the ocean. It uses ocean temperatures, ocean pressures. It doesn't use toxic materials, and it doesn't add toxic materials back into the environment. What a great manufacturing technique. So I've been fascinated with how biology's evolved to make materials, and this is a picture of the abalone shell, and if you look at it in scanning electron micrograph, what you'll see is that it's made out of these nanostructured materials of calcium carbonate. And this is part of the secret on why it's 3,000 times tougher than its geological counterpart. There's two. One is nanoscale, regularity, and the other is evolution, because this organism evolved over, or organisms of the ocean evolved over 500 million years in order to make these materials. And they use proteins. They have a DNA sequence that codes for proteins. They make these proteins which can grab calcium and carbonate out of the ocean, out of the environment, and start putting down these really precise molecular structures. And so what I've been interested in is, well, what about the rest of the periodic table? So organisms in the ocean have used calcium carbonate, silicon, iron oxide is some of the most calcium phosphate materials that they use to grow with from the periodic table. So what if you could have organisms work at the whole periodic table? What could you make using biological approaches? So what you'd be getting is materials that can evolve to become better over time, and materials that are made under environmentally friendly conditions. And so this is a picture of a M13 bacteriophage. It's a virus that has 2,700 copies of a protein that make it up. So it's protein covering DNA sequences. And these proteins are crystallographically aligned. So now you can imagine going in, using a library of 1 billion different viruses, and choosing the ones that could work with anything you want on the periodic table. Let me grab some examples from over here. This is an example of a battery that's a sodium ion battery that's made with bacteriophages. We evolved the ability to make cathodes and anodes, and you could make battery electrodes out of them. So I was part of a DARPA program called the 1,000 Molecules Program, which is an amazing program that was using biology to make molecules that you would make in different ways or normally not made biologically. I was one of the only material scientists on this program, and I got to make materials. So my group made at least 110 different materials, and we used them for energy storage, and these were materials for energy storage, catalysis, environmental remediation, solars, magnetic materials, and toxic materials. So we made over 100 materials, and we down-selected to two major types. One was using biology to make materials for batteries that could be used for UAVs. So these were solid, flexible batteries that were used for UAVs. And the other was toxic chemicals. So what we did was we genetically engineered these bacteriophages, these viruses, to use the chemistry on the surface to make high surface area carbons. And so this was our down-selected material. I thought, really, after all this, we picked carbon? But this is a carbon material that that is made by viruses. It's templated by viruses. It has so it's about 2,000 meters squared per gram. So it's a very high surface area material. And when we first developed it, we were developing it for battery electrode materials and some other applications in batteries. But what we found is that it was really good at binding small molecules very rapidly. And so we said, what else would that be used for? And so we used it, we were collaborating with the Army labs to use it for very toxic materials. And so we found that we could make these materials. They were really great at doing toxic materials that the warfighter may encompass. We made them in different form factors, including textiles, wipes, shampoos, filters that could filter both chemical and biological toxic materials. We've spun out a company to look at binding and neutralizing PFAS, for example, out of water. And basically, working with CCDC, CBC, Army labs, we're able to make it into many different form factors, use it to to look at masks as protection for not only chemicals but biologicals. And one thing that we recently worked on the Army with was it actually is really good at also binding and holding on to and storing gases. So this is oxygen and air and CO2, and we're also looking at methane. But we're looking at it as a new form factor for backpacks or a way to store air or oxygen for the warfighters. So I'm exactly out of time with that. Thank you for your attention. It's been an amazing program to be a part of. And I'll be happy to take questions outside after the session. Thank you.